Good day, this is Dr. Wortel with a discussion on Worksheet 13. So let us start with the first question. Okay, so we have to evaluate this triple integral. Thankfully our region E is quite nice because it is a so-called rectangular box. So the only thing that's maybe slightly difficult is this absolute value. But of course we can rewrite this. Because the absolute value of y being less or equal than 1 just means that y is between -1 and 1. So x is between two boundary values, y is between two values, and z is between two values, so it's a rectangular box. So we could use any of the 6 possible orderings. Well, let's do x first. So x is from 0 to 1, then y from -1 to 1, and then z from 0 to 2, y plus z. So z dy dz dx. Okay, so what we have to do is look at the inner integral and integrate it with respect to z. So leaving the x and the y unchanged. Now we have to integrate y plus z with respect to z, so that's going to be yz plus z squared over 2. And the boundary values are 2 and 0. And we leave the dy dx. So now we leave the outer integrals, we plug in 2, so then we get 2y. Remember, we integrate with respect to z, so we plug in 2 for z, so we get 2y plus 2. And if we plug in 0 for z, we get 0, so I won't write that down, and I have my dy dx. And now what we have to do is take again the inner integral, and this time we integrate it with respect to y. So we get the integral from 0 to 1, then the integral of 2y plus 2, that's going to be y squared plus 2y. The values are 1 and -1, dx. So first we plug in 1 and then we get 1 plus 2. Then we plug in -1, so -1 squared is 1, and 2 times -1 is -2. So that's 1 plus 2 is 3, and that's -1, so that's 4. 3 minus -1, that's 4. And then you can either work it out yourself, or if you sketch it, you see that this is a area of a 4 by 1 rectangle. So that is 4. Let's continue with the next question. So the next question is a little bit more difficult, because now we don't have a nice rectangular box, but we have a region which looks more complicated. So the question asks us to use a type 2 integral, and that means that we have to look for that x is the first variable over which we integrate, and we're going to have to look at the shadow on the yz plane. So let me first try to sketch the region. Now this is a little bit tricky because there are so many equations, so we should first think about what the equations mean. Okay, so we have two equations, x and 1 and x equals 1 and x equals 3, and these are going to be vertical planes, but these will not intersect the yz plane, because the equation of the yz plane is x equal to 0. So let's first focus on the other three equations. So these other three equations have no x in them, which means that it's going to look the same for every x. Since I want to compute the shadow on the yz plane, let me first draw just these three equations on the yz plane. So first, maybe I should do that in blue. So this is the y-axis, the z-axis, and the x-axis. So y equals 0, that's in the yz plane, looks like this line over here. So that's y equals 0. Then z equals 1. Z equals 1. And then we have y equals z. Yeah, this unfortunately goes over the x-axis a little bit, but the x-axis goes into the depth, and these things are in the yz plane. Now I've drawn a bunch of lines, and these things are planes, but here what I mean is that these things don't depend on x, so this is for x is 0, I've drawn them for x is 0, and for every different x we have the same picture. So in particular, we say that the shadow on the YZ plane here is this triangle over here. Maybe we should write this in a separate YZ plane over here. So the YZ plane, this is our shadow on the YZ plane, and that is over where we're going to integrate. Now we have to think a bit about these equations x equals 1 and x equals 3. So they are going to be horizontal planes. By what I just said, this figure over here is going to repeat for every x. So for instance, for x is 1, maybe I should do that in, let's do that in green. For x is 1, I'm going to have a triangle like this in the same way. So that's at x equals 1. And at x equals 3, I'm going to have the same triangle. So maybe let's draw the final figure in red. Since it's the same, since it's going to be between x is 1 and x is 3, it's going to be everything between these two triangles. And remember again, the triangles are the same for every x, because these equations do not depend on x. So let's try to fill this in with red. So we've got... we've got the red area between the two green triangles. That is the part that we are integrating over. So in these types of questions, this is often the most difficult part, is to figure out what's going on and how to convert the equations into a picture, and to take into account that if one variable does not appear, it means that the equation does not depend on that variable, and therefore it will look the same for whatever value that variable has. So in this case, the x value does not appear in these three equations, so the picture, the triangle, looks the same for every x value. Okay, so now we can have the triple integral over region E of e to the z squared dv. Because it's type 2, can now be written as the double integral. Let's call this thing a triangle, so let's call this region T. And then the integral from 1 to 3, that's x, e to the z squared dx. And then we have a dA from the triangle T. So often in these type of questions, before we even write this down, we can already split up y and z. In this case, it's a little bit more convenient to wait, and I will explain now. So let me first compute the inner integral. So the inner integral is going to be, that's going to be x e to the z squared between the boundaries 3 and 1. And if I plug in 3 and then subtract 1, I will get a 2. So now we have to decide, we're left with a double integral, and we have to decide whether to do it type 1 or type 2 in the yz plane. So the reason that I computed this first instead of making a choice now is that if I look carefully here, you can see if I pick the order dz dy, I'm going to have to integrate this with respect to z. However, e to the z squared, we know there's not a good formula for this. There's no way to integrate a formula for this. So we can already see that we should probably do dy dz. Yeah? And therefore, we should do this triangle here. So we want to do dy dz, that means it's going to be type 2 in the yz plane. Let's write this down. Type 2, and remember this is the yz plane. So that means first we need to figure out what the bounds for z are. Well, we can see that the z goes between 0 and 1. So z is between 0 and 1. And then y, this is the start curve. This is where y equals 0. And this is the end curve. This is where y equals z, right? Because z equals y. Let's write this down. This is the curve z equals y. And this is the curve y equals 0. So y is from the start curve, which is 0, and the end curve is z. Alright, so let's continue over here. So we decided we want to do this as type 2, so the integral from z from 0 to 1, and y is going to be from 0 to z, 2 e to the z squared dy dz. Right, and again, if we had dz dy, we would not be able to integrate this here. This is why I chose type 2. Okay, so let's compute this integral. So we integrate with respect to y, so this thing is a constant, so I just get that times y, so I get 2y e to the z squared between the boundaries z and 0, dz, which is 2z e to the z squared, dz. And whereas before over here we had something that we could not integrate with respect to z, here we can, because we see that the derivative of z squared is 2z. So you can use substitution, or if it's also okay to directly see that this is just e to the z squared between the boundaries 1 and 0, right? If I differentiate this, I will get e to the z squared, and by the chain rule I get a 2z. So that's exactly that. Which is e to the 1 minus e to the 0, so the final answer is e minus 1. So let us continue with the final question. Okay, so again we have a more complicated region above the xy plane and below a certain surface. So again, first we have to sketch this, because this is the only way that we can figure out what's going on. Y, x, and z. Okay, so below this surface, well, if you go back to chapter 1, you know that z equals square root of x squared plus y squared is a so-called circular cone. Now we don't have that, but you have 1 minus that. So minus that means that it goes downwards, and 1 minus that means that it starts at 1. So it starts at 1 here, and then there will be a circular cone going downwards. So that means it's going to hit the xy plane in a circle over here. And it's going down like this. Right? And so we know that our region is above the xy plane. So the shadow on the xy plane is a circle, which is our region D. Let's write this down. So if you're not sure on how to sketch this, please go back to chapter 1, and then you can see how you can sketch such a region. All right. So now we can start computing the integral as a type 1 integral. As you can see from the picture, since it's above the xy plane, so the bottom surface is where z equals, where is the xy plane. This is the equation where z equals 0. So that's our region D. So that's the start region. And the top surface is going to be where it hits the circular cone over there. So it's going to be an integral from 0 to the circular cone. So we're going to integrate over the shadow, which is D. And then we have an integral from the bottom surface, which is 0. That's the region D. And the top surface, which is circular cone, given by the equation where z equals 1 minus the square root of x squared plus y squared, and the integrand is 1 plus the square root of x squared plus y squared dv. Okay. So again, we could first compute the bounds for x and y, but if you look at the shadow on the xy plane, it looks like a circle. So it already looks like we should probably use polar coordinates. Whenever you want to integrate over a circle, it usually makes sense to do polar coordinates. So let's, in this case, again, first compute the inner integral. Apologies, I forgot the dz. This should not be dv, but this is now dz dA. So let's first compute the inner integral, and then see what we get. So leaving the outer integral, we get, okay, we have to integrate this with respect to z, but this is a constant. So we get 1 plus square root of x squared plus y squared times z. From the bounds 0 to 1 minus the square root of x squared plus y squared dA. Well, for z is 0 we get nothing, and for the other one we just plug in that equation. So we get 1 minus the square root of x squared plus y squared dA. Now this is of the form a plus b times a minus b. So that's equal to a squared minus b squared. So that's 1 squared, which is 1. And the other thing squared is just x squared plus y squared. So now let's look at how to compute this. So as I just explained, we're integrating over our region D, which is a circle. So this is my region D. So it makes sense to use polar coordinates. And indeed, we can see here that it's very convenient because if you remember in polar coordinates, x squared plus y squared is just r squared. So the integrand is very easy. And also our circle, as you know, is very easy to parameterize in polar coordinates. So let's do that over here. So that means the theta is between 0 and 2 pi, because it's the entire circle, and the radius is between 0 and 1. Yeah, so let's continue this in blue. So theta from 0 to 2 pi, the radius from 0 to 1, then you have the integrand, which is 1 minus r squared. Of course, don't forget the extra r, the Jacobian, dr d theta. So what we get is just r minus r to the third. Well, that's easy to integrate with respect to r, because that's going to be r squared over 2 minus r to the fourth over 4, between the bounds 1 and 0. So what do we get? We get a half minus a fourth, which is a fourth. And now again, well, this is just going to be 2 pi times 1/4, so you can compute that yourself, or you can see that this is just pi over 2. So one final comment is that basically what we've done here, if we've used cylindrical coordinates, but this worksheet was not about cylindrical coordinates. But you can see here that the method is sort of the same, because we start by integrating z, because we see that, okay, we have to do it from this one to that one, from this surface to that surface. So we integrate out z, and then we turn the x and the y into the r and the theta. And that's also how cylindrical coordinates work, because in cylindrical coordinates the z is preserved and the x and the y is turned into r and theta. So this is, if you want, you can think of this as a different take on how to do cylindrical coordinates. So that's another way that you can think about this exercise.